So, hello everyone. I would like to welcome you all to our talk on how Bloomberg creates a resilient data analytics platform on Karmada. My name is Ilan, and I'll be speaking with my colleague Michas, who works with me at Bloomberg on cloud-native data analytics infrastructure. To kick things off, I would like to walk through the agenda for today's talk. We will begin by giving a short introduction to Bloomberg's data landscape and how our organization has built the data analytics platform spread across multiple Kubernetes clusters, and the challenges that we have encountered in operating in such a platform. And then we will talk in depth about how Karmada has functioned as a solution for Apache Flink and poses as a promising fit for solving the challenges in Trino and Apache Spark. And lastly, we will close out by highlighting the ongoing improvements within the community. So when looking at Bloomberg's data landscape, the key thing to highlight is the importance of Bloomberg's commitment towards providing extremely reliable, robust, and accurate data products. These products operate at huge scale with massive growth and spread across various data cataloging solutions and are ingested and explored with various analytical compute engines. To highlight some of the managed offerings that Bloomberg provides within its data analytics ecosystem, these include Apache Flink, which is a distributed processing engine for data streams that uses data stream APIs for its real-time processing; Trino, another distributed compute engine for interactive and batch exploration that uses ANSI SQL APIs for its querying; and Apache Spark, a third distributed compute engine for batch ingestion and interactive exploration that uses data frame APIs for its analytics. Putting these analytical engines together, what you see on the screen is an example of a data analytics pipeline that a data engineering team may manage for their business use case. As we provide these data analytics pipelines for our teams, building a scalable, self-service, reliable, and multi-tenant platform is critical. Kubernetes provides an extremely powerful compute, networking, and scheduling abstraction on top of heterogeneous hardware types, and we rely on it heavily to both operate our platforms and teams with the right separation of concerns and ownership. By leveraging Kubernetes and an observability layer like Prometheus and Grafana, the platforms can solely focus on operators that govern platform-specific CRDs, like a Spark CRD, a Flink application CRD, or a Trino CRD, and rely on lower infrastructure substrates to provide the necessary platform tooling to allow for their platforms to scale across multiple clusters. But given the current feature set that Kubernetes provides, these data analytic platforms are limited in what they can provide for their users. And to talk about what challenges exist for our platforms at the moment, I'll hand it over to Michas.
Cool. So as you can probably imagine, managing a growing data analytics platform comes with its own set of challenges. When the platforms were first created, we didn't have a sophisticated job management system. Users would apply their jobs using kube configs that mapped to a single cluster. But since users are deploying across multiple clusters in multiple environments, this quickly becomes unmanageable. Additionally, the issue is even more noticeable when we're trying to do cluster maintenance. Generally, it's not recommended for users to be running their workloads actively on a cluster that's undergoing maintenance, such as a Kubernetes upgrade. And this requires a lot of coordination between the user and the platform. Lastly, disaster recovery itself is not trivial. Services and applications must recover gracefully in the event of failures, but without any automated failover mechanisms in place, this puts a lot of responsibility on the user, something that should be taken care of by the platform. Additionally, stateful recovery is even more complex, which we talk a bit about during the Flink use case. So a lot of these challenges are centered around our platform running in a multi-cluster setup, but requiring users to be aware of individual clusters. Ideally, our users are application experts, and they want to start running their data pipelines without having to necessarily worry about what Kubernetes is or which cluster they want to deploy to. As a result, we started to think about how we can introduce some sort of federated layer to abstract this away. When we were in our ideation phase, we started to think about the user and platform requirements. From the user side, the primary requirement was that job deployment and management was easier. In addition, they expected that regular maintenance would happen without disruption. And additionally, they expected that the platform would be more stable and provide application uptime guarantees through features like automated cluster failover. On the platform side, the requirements end up being quite similar. We wanted cluster management to be simpler. Additionally, we wanted to provide better platform stability and also optimize our hardware utilization. So as we started to flesh out these requirements, we started to look for open source projects that could help us out. And this is how we were introduced to the Karmada community. Karmada, for those who are unaware, is an open source Kubernetes management system that helps platform owners and users run their jobs across multiple Kubernetes clusters. In addition to cluster management and workload propagation, Karmada comes with a bunch of other useful features such as global resource view, unified authentication, and of course, cross-cluster failover. So starting with the Apache Flink use case, before I start talking about how we used Karmada to tackle these challenges, I wanted to provide a quick overview of what Apache Flink is. Apache Flink is an open source stream processing framework that specializes in building real-time data processing applications. Apache Flink provides users with the ability to handle very large data scale, in addition to providing very low latency processing. Depending on how these pipelines are configured, users can enjoy exactly one's processing guarantees, which are backed by Apache Flink's state management. Since our data platform runs on top of Kubernetes, it was important to integrate Apache Flink with that environment. And so our platform relies on the open source Flink on Kubernetes operator, which manages the Flink lifecycle through the use of a Flink deployment CRD, which you'll be seeing throughout the presentation. And lastly, with long-running jobs, it's important to understand that errors can and will happen, so providing auto-recovery mechanisms is pretty critical. Luckily, Apache Flink on Kubernetes comes with auto-recovery features, which can be configured through Flink deployment's high availability settings, which will allow these applications to self-recover in the event of hardware failures, OOMs, or network glitches. So using this basic understanding of Apache Flink, we can start to get into what the platform requirements were for integrating with Karmada. First, we needed to have a unified endpoint through which Flink deployments could be applied and managed. And luckily, this is provided by Karmada out of the box. Secondly, we needed to help Karmada interpret what a Flink deployment actually is. This is critical for integrating with Karmada, since Karmada needs to understand the resource requirement, but also the health of the application for failover purposes. Once Karmada understands the resource, we needed to handle how to conserve state between cluster failovers to make sure that failover is graceful. And lastly, to ensure failover clusters have sufficient space, we needed a way for Karmada to directly enforce quota limits. So the last 3 points are something that we had to actually work on. So starting with Karmada's actual scheduling, so we'll be using a unified endpoint to schedule and manage Flink applications. And for those unfamiliar with Karmada, the way that this works is by using a Karmada native CRD called a propagation policy. Propagation policies provide Karmada with instructions on how to actually schedule your resource. And this can be as simple as defining a single cluster affinity and scheduling via a label, or having a more sophisticated approach via spread constraints or application priority. But this propagation depends on Karmada being able to understand the resource. There's already support for native Kubernetes resources, such as deployments or stateful sets, but CRD interpretation requires additional work. Luckily, Karmada provides an extensible interpreter interface, and this allows users to define implementations for specific methods they may need. For the purposes of this presentation, we're going to go over interpret replica, which determines how many replicas Karmada is scheduling, in addition to interpret health, which allows Karmada to parse the resource status and make decisions on the health of the resource. Now, to better understand a resource interpretation, we're going to walk through an example Flink deployment spec. This is a paraphrased spec, but shows some of the important parts. So above, we can see the highlighted job manager and task manager definitions. So these are required fields for users to define when applying their Flink deployment, since it tells the Flink operator what the resource requests and limits will be for the job manager and task manager components. And even though we know what the resource footprint is, we still need to figure out how many pods in total are going to be scheduled. This can be deduced by looking at the job parallelism as well as the number of task slots. So for example, if we have a parallelism setting of 4, with each task manager receiving 2 task slots, then that results in 2 task manager pods plus the number of job managers, which in this case is just 1. So that gives us 3 pods. We can represent this with a couple of simple formulas. The total number of replicas we've just gone over, but we also need to take a look at the individual resource footprint for one replica. Since Karmada does not currently support multiple pod template support, we needed to do an estimation, which is just the max of the CPU and memory for each individual component. This does provide an overestimation of the total resource usage, but it gives us the guarantee that when Karmada schedules the resource, the cluster will for sure have enough capacity to spin it up. So here are our results. And you may be wondering, where does this interpreted resource requirement actually go? This information will get added to the resource binding, which is a Karmada custom resource which contains important metadata on the resource being scheduled. I like to think of it as kind of the source of truth for your resource. And we can see our replica requirement and count has been populated. But now that Karmada can decide how to schedule your application based on this replica count and requirement, this is great. We can essentially ensure that applications will get evenly spread across clusters. But because we're also relying on Karmada's failover features, we need to tell Karmada how to interpret the health of the resource. So Karmada provides two forms of failover. For the purposes of this talk, we're going to focus on application level. This is primarily figured out by the custom interpreter, which uses get health, and it determines whether the application is healthy. If it's unhealthy for a certain period of time, if it goes beyond the toleration, the application will get rescheduled. For cluster failover, we directly ping the Kubernetes cluster API server using the health endpoint. If you guys have more questions on this, just come up to me afterward. I can give you a more thorough overview. So how do we tell Karmada how to determine when an Apache Flink application is unhealthy? For us, we decided to take a look at the Flink internal state, which provides a key indication of the overall health and status of the pipeline. But the question for us was, how do we differentiate between user errors and cluster level errors? For us, the key was using the ephemeral Flink states and treating those as unhealthy, so reconciling, initializing, and created. Those are the blue states in the simplified state diagram. And those indicate that the Flink job is still trying to launch. But the Flink state itself only provides an estimation. It by itself is not enough. We need to also take a look at the actual error field, which is also populated in the Flink deployment status. These error fields usually display deployment level errors. Think about like bad image definitions or missing required fields, or crash loop backoffs. In those cases, we want to ignore this, since Karmada will just continue rescheduling these applications and cause a lot of churn. So here's an example. Flink deployment status shows us running in a running state. So we're good. This is healthy. But additionally, this is a case in which the Flink state is reconciling, but there's a clear error here. And it's the user defined a bad image that's unable to get resolved. In this case, we treat this as healthy because it's a user error and they can fix this themselves. Lastly, this status shows a created state without errors. This may be due to the job manager being unable to spin up task managers, possibly due to the cluster not having sufficient resources. So in this case, the application is treated unhealthy, and if it does not recover in time, it will get failed over to a new cluster and spun up there. Cool, so now our resource binding has all the information it needs to correctly interpret a Flink deployment. With the new health status, it can determine when to fail over an application. Now in this diagram, we take a look at an example failover. A Flink deployment is stuck in reconciling state for longer than Karmada can tolerate. And after that happens, it'll delete the application and reschedule it to a new cluster. But what we notice is that since it's deploying the same spec, the application starts as new. And this is a huge problem because a lot of our users run stateful processing pipelines, and they cannot allow for reprocessing of data and duplicate data points in their sinks. So we need some way to conserve state between failovers. So by working with the Karmada community, we were able to introduce a new feature into Karmada's failover, which allows Karmada to conserve pieces of state between failovers. So for Apache Flink, this state can be found by using the Flink cluster's job ID, which points to a checkpoint that could be stored in an external data store. And if we conserve this job ID, we can ensure that Apache Flink applications can gracefully resume from their previous state, since we have a pointer to the latest checkpoint. But how do we actually plug this in using the state preservation feature? So the first thing is we need to use a JSON path. It's just an expression that targets a specific piece of data that will be conserved between failovers. In this case, we select job status.jobID. And then secondly, we just decide on an alias label name, which will be the name of the injected label into the Flink deployment. So in our finalized diagram here, we have the same case that we had previously, where a job is stuck in reconciling. After the toleration is elapsed, Karmada will parse out the job ID out of the Flink cluster's status. It'll delete the resource, and then when rescheduling, it'll actually inject that information as a label into the new resource. We have a Caverna webhook that intercepts this request and fetches the latest checkpoint information for that Apache Flink application, and then we'll set the initial save point path from which the Flink operator will be able to start the application from that latest state. And so now we've been able to add support for customized Flink deployment resource interpretation, as well as stateful failover between clusters to ensure graceful restarts. But with failover, we still need to carefully consider how to track and limit resource quota usage. Take, for instance, we set a resource quota on each member cluster that has 20 CPU and 50 gigs of memory. Karmada will decide to schedule or continue scheduling applications until there's no longer any space available on either cluster. But this has implications on cluster failover. Let's imagine that member cluster 1 has some sort of failure. In that case, Karmada will eventually evict applications from that cluster and try to reschedule them to another cluster. But the rescheduling won't work because the resource quota is totally full, essentially rendering failover useless. So the solution here was to enforce quota usage not on a member cluster level, but directly on a federated level. So using the federated resource quota, which is another CRD in Karmada, we can now enforce quota limits directly on a Karmada control plane level, ensuring that the total resource usage across all clusters will only be 20 CPU and 50 gigs of memory in this case. And this is great because it means that Karmada is able to ensure that there's sufficient capacity on the other Kubernetes clusters, greatly simplifying the planning that we need to do as platform owners. Please note this is a new feature that just came out, so you will need to enable the federated quota enforcement feature gate. And so now, just to recap, besides providing a unified endpoint for job deployment and management, we were able to integrate Apache Flink with Karmada by, one, adding support for Flink deployment CRD interpretation, specifically resource interpretation and health interpretation. Two, by adding support for stateful failover to ensure stateful Apache Flink applications can gracefully resume in the event of failovers. And then lastly, adding support for federated quota management. In the next section, Ilan will discuss how Karmada can solve these challenges of federation for both Trino and Spark.
Thank you, Michas. So now looking to the next platform within our data analytics stack, we have Trino. So what is Trino? Trino is a scalable and highly distributed query engine that optimizes query performance through parallel processing and predicate pushdowns that is typical of a distributed data analytics tool. But also through distributed caching, it helps avoid redundant reads and when repeatedly accessing an object. Trino is also an ANSI SQL compliant engine that interacts with popular open source business intelligence tools and is also a versatile engine that provides support for ad hoc analysis at both interactive speeds and multi-hour batch workloads. So in KubeCon EU of this year, the link can be found in our slides, our colleagues at Bloomberg, Sung and Aki, introduced the custom resource to help simplify the workflow for Trino service owners. Now take note on how simple the spec is to define the data catalogs you wish to bind to your service and the limited configurations needed for setting your resources. Now I won't go into the details of the spec as that was covered in the previous talk, but I encourage you all to go check it out. But what I would like to highlight is another slide from that talk in which we show the resulting status from applying that Trino service custom resource against the Kubernetes cluster, say Trino Devo 1. Now it's worth to note here that behind the scenes, the Trino service controller spawns a sub-resource called the Trino deployment, which contains all the coordinators and workers that make up a Trino cluster. And this deployment outputs back the Trino service status, the resulting endpoint that can be queried with SQL. Now the common method of querying Trino is to use a Trino CLI or some dashboarding tool like Superset. Now I'm showing an example here where you would put the resulting query endpoint from the status into the Trino CLI directly, but what is important to note in this demonstration is that the sub-resource Trino deployment that is being created is bounded to a particular Kubernetes cluster, Devo 1 in this example. But what happens if I want to move to a state where this endpoint would actually be spread across a multitude of kube clusters across the dev tier, say Devo 1 or Devo 2, but we want to have a clean interface like this where it's just -dev at the endpoint. So given this goal and seeing all the primitives and enablements of Karmada, especially the ones that Michas had walked through earlier, we can see how Karmada is a natural fit for providing a unified endpoint to query. As such, enabling Trino to run on Karmada requires the following checklist. Now take note that this is really similar to what Michas was discussing earlier. So the ability to have a unified endpoint for job deployment and management comes for free with Karmada, but what needs to be implemented is the Trino deployment within the resource interpreter webhook so that a resource binding can be used to bring back aggregated status, and so propagation policies can be made to apply custom strategies for deploying Trino clusters. And lastly, thanks to the recent merging of the federated quota enforcement, this also comes for free with Karmada. So putting this together visually within a step-by-step workflow, we see that a service owner would create a Trino service, which is responsible for returning that unified endpoint and overall status to the user. But behind the scenes, it submits a Trino deployment to Karmada and leans on Karmada's federation and scheduling to propagate and reconcile the Trino deployments against the workload clusters. So after reconciliation and receiving a list of endpoints and healthy statuses of Trino deployments, Trino service will then configure against the gateway those two endpoints and receive a federated endpoint it will return to the user. So a platform user would then run Trino queries against that federated endpoint, and the gateway would query the appropriate endpoints. So drilling into the submission logic of Karmada, we will use that Karmada federated endpoint for submission, and after introducing the Trino deployment to the resource interpreter webhook, we can then use the resource binding to display aggregated status. Drilling into the propagation of Karmada, for Trino, we decided to start out with a simplified duplicated replica scheduling type for Trino deployments, as well as helper resources like secrets. In the future, we want to extend it to have more complex scheduling strategies around, say, deploying to 2 out of 3 data centers. Now, that's all possible with more complex propagation policies. Drilling into the reconciliation of Karmada resources, Trino service will leverage resource bindings that will populate the deployment health and endpoint URLs of the Trino deployments. So with Karmada enabling key features in Trino, let's now look at the last platform within our data analytics stack, Apache Spark. So what is Spark? Spark is a distributed compute engine designed for large-scale data processing, where when it is compared to the competitors in the batch ingestion space, say at the terabytes to petabyte scale, it really shines. It supports batch and interactive workflows, has connectors for many file formats and data sources, and because it partitions data automatically, it makes it a great fit for cloud object stores. Its data frame and SQL APIs make it a very powerful tool for data engineers as well. At Bloomberg, we classify Spark to serve 2 different purposes: interactive exploration and batch ingestion. Spark Interactive provides an interactive experience similar to Trino using data frame APIs. As such, we find the use case to be a fit for those who are doing interactive analysis, needing more lenient SLOs, and are able to run in a heavily over-allocated cluster. At Bloomberg, we define the custom resource definition called connect sessions, which simplifies the complexity in setting up an interactive Spark session. Spark Batch provides a batch ingestion framework for runs and completion workloads that could use a mix of data frame and SQL operations. As such, we find the use case to be a fit for those who are doing batch ingestion, needing strict production SLOs, and requiring only once guarantees and data locality when possible. At Bloomberg, we define a custom resource definition called Spark Job, which simplifies the complexity in setting up a batch Spark application. So we will kick it off by walking through the use case of Spark Interactive. This in itself deserves its own talk, but we will keep this at a higher level, but still allow for the Karmada use case to be clear. So to define how Spark Interactive works, we must understand how Spark Connect works, which underpins the Connect sessions functionality. So the user begins by initializing their Spark session in the Jupyter Notebook, and this will create a corresponding driver pod on the Spark cluster. Then with the Spark session, the user can execute Spark code, and it will get sent as an unresolved logical plan to the Spark driver via gRPC. In the driver, the unresolved logical plan gets translated into Spark's logical plan operators, and then gets optimized and executed. The results are then streamed back to the client through gRPC as Apache Arrow-encoded row batches. The endpoints that the user would send unresolved logical plans and receive PyArrow batches is highlighted here, and is configured in the Spark cluster by a whole host of resources. And the sending of the logical plan and the row batches is handled by the PySpark client. Now, to simplify the complexity of setting this up, we have introduced the custom resource called the Connect session that wraps up this logic in a simple yet powerful abstraction. This is an example of a Connect session that we are introducing. Now, please note how simple the spec is in defining the data catalogs you wish to bind to your service and the limited configurations needed for setting your resources. Now, I won't go into the details of the spec as that deserves a separate deep dive. But what I want to highlight is a very similar story to Trino, and that when a Connect session custom resource is applied to a Kubernetes cluster, say Spark Devo 1, that behind the scenes, the Connect session controller spawns a variety of resources that include the driver and executors that make up a Spark cluster. And at the success of the cluster's creation, it would output back to Connect session status the resulting endpoint that could be queried with SQL or data frame APIs. Now, the common method of querying Spark is to use a PySpark client as shown here. And I'm showing an example here where you would put the resulting Connect endpoint from the status into the PySpark client directly. What is important in this demonstration is that the Connect session that is being created is bounded to a particular Kubernetes cluster, Devo 1 in this example. But what happens if I want to move into a state where this endpoint would actually be spread across a multitude of kube clusters, across the dev tier, say Devo 1, Devo 2, but to have a clean interface, like in Trino, where it's just -dev at the endpoint? So given this goal, very similar to Trino, we can see how Karmada is a natural fit for providing a unified endpoint to query. Now take note that another abstraction similar how Trino service spins up Trino deployments is needed here. So here we have a connect service which spins up connect sessions. Spark Batch, on the other hand, has a different submission strategy. With the run to completion code packaged into the image, the complexity of spinning up the Spark cluster and running the application code is simplified with a Spark job custom resource. Here, however, the platform wants the service owner to submit the Spark job to a workload cluster that is less busy to ensure proper hardware and resource utilization. The service owner, however, wants scheduling to be done intelligently, with centralized status management and with the possibility to co-locate their compute with their storage whenever possible. Given these considerations, Karmada is a natural fit to provide these capabilities. As such, enabling Spark to run on Karmada requires the following checklist. Now take note that this is very similar to Trino and what was discussed earlier by Michas. So the ability to have a unified endpoint for job deployment and management comes for free with Karmada, but what needs to be implemented is the connect session and Spark job within the resource interpreter webhook so that a resource binding can be used to bring back aggregated status, and so propagation policies can be made to apply custom strategies for deploying Spark clusters. But uniquely from Trino and similar to Flink, we will need to introduce a resource interpreter for Spark jobs so that custom resource-aware only one scheduling can be done. And lastly, thanks to the recent merging of the federated quota enforcement, this once again comes for free with Karmada. So putting this together, let's visualize this for Spark Interactive within a step-by-step workflow. We see that a service owner would create a connect service, which is responsible for returning that unified endpoint and overall status to the user. But behind the scenes, very similar to Trino, it will submit a connect session to Karmada and leans on Karmada's federation and scheduling to propagate and reconcile the connect session against the workload clusters. After reconciliation and receiving a list of endpoints and healthy statuses of connect sessions, connect service will then configure against the gateway those two endpoints and receive a federated endpoint it will return to the user. A platform user will then run Spark queries against that federated endpoint, and the gateway would query the appropriate endpoints. Drilling to the submission logic of Karmada, we see something similar to Trino, where we'll use the Karmada federated endpoint for submission, and after introducing the connect session to the resource interpreter webhook, we can then use the resource binding to display aggregated status. Drilling to the propagation of Karmada, we will see something similar to Trino, where we decided to start out with a simplified duplicated replica scheduling type for connect sessions, as well as helper resources like secrets. And drilling to the reconciliation of Karmada resources, also similar to Trino, connect services will leverage resource bindings that will populate the deployment health and endpoint URLs of the connect sessions. Now let's visualize this for Spark Batch. Within a step-by-step workflow, we see that a service owner would create a Spark job against Karmada, which is responsible for returning the status of the job and an endpoint, in this case the Spark UI, back to the service owner. As such, we will continue to lean on Karmada's federation and scheduling to propagate and reconcile the Spark job against chosen workload cluster that has the most capacity while adhering to the quota limits. So drilling to the submission logic of Karmada, we will use the Karmada federated endpoint for submission, and after introducing the Spark job to the resource interpreter webhook, we can then use the resource binding to display aggregated status. Drilling into the propagation for Karmada, for Spark jobs, we're using a more sophisticated propagation policy to achieve that only once and data locality. This will require the usage of spread constraints to be min-max one cluster, and for cluster affinities to be set to default to a co-located cluster when possible, given the cluster capacity and health. And we will continue using duplicated strategy for helper resources like secrets. And drilling to the reconciliation of Karmada resources, Spark job would leverage resource bindings that would populate the workload success and failure and endpoint URLs of the Spark UI of the workload. So we have now gone through a few case studies of how Apache Flink, Trino, and Apache Spark use Karmada. I'll hand it back over to Michas to close out on how this all comes together.
Cool. So the key takeaway here is that with the help of Karmada, we've been able to provide a unified management layer for a variety of different data applications, be it Spark, Trino, or Flink, which not only makes job deployment easier for our users, but also provides additional key requirements such as better application resiliency, thanks to cluster failover, and resource utilization, thanks to resource-aware scheduling, just to mention a few. Going back to our original user and platform requirements, we can see that Karmada has been able to check off all of our boxes here. The unified endpoint provided by Karmada greatly improves the ease of job management for the user, while the Karmada cluster management improves our lives as platform owners by making maintenance and reacting to disaster scenarios a bit easier. Additionally, the extra features, as I've mentioned before, such as automated failover and resource-aware scheduling, help provide our users with a more stable experience and help us define better platform SLOs for our users. Now, we've made a ton of progress, and I've worked with the community to add support for a variety of features that we went over today. Most notably, the state preservation, which was added back in 1.12, which we use for Apache Flink, as well as the new federated quota enforcement feature, which has just been added to the latest 1.14 release. But there's always more work to do, and we're excited for some of the efforts being worked on in future releases, such as the improvements to cluster failover, as well as the introduction of multiple pod template support, which will provide better pluggability for CRDs with multiple components. And then lastly, I just wanted to share the Karmada community is active and growing. If you're interested in contributing or just have questions about how Karmada works, please reach out to us on Slack or on our GitHub. And that's it. Thank you so much for coming.
We can repeat the question here.
Thank you. I see you create some customized CRD like Spark jobs and Trino service, and these CRD are all under the Bloomberg title, I think. I don't know how did you convert this CRD like Spark job to a real Spark pod. Usually I think we need an operator or something to consume the creation of the CRD and then create a real pod. For example, if you want to change the pod stack, how can you do that? I don't know if there's any logic in a Karmada or some other place you need to do. Yeah.
Really good question. So let's section that into different subsections. If you're introducing custom resource definitions, obviously you need those operators to exist. So we have operators internally that have been running, and we presented last KubeCon a Trino operator that we're looking to open source with the community. The Spark operators, we've presented a few times at different conferences, but we're working to open source that as well as there's a lot of momentum now with Apache Spark having its own operator that's going to be done with the community. When it comes to Karmada, the beauty of kind of the flexibility that's being provided by introducing the resources into the resource interpreter webhook is that it's very flexible to bring your own CRD, and so it's able to conform quite nicely in that ecosystem. And so it's quite flexible with custom resources that people provide.
Oh, yeah, thank you.
Any other questions?
So how does Karmada monitors? You said that the jobs that you're submitting, they are like sent to the different clusters. So how does it monitors the health and the usage, like how many resources are available, or does it schedule the jobs on multiple clusters parallelly, or just goes to one cluster?
So the Karmada scheduler, it's just a single queue. So the scheduling will take place application by application. When it comes to, I guess, like the monitoring of the application, each individual Kubernetes cluster is responsible for publishing those metrics or, let's say, logging, for example. So that's actually independent of Karmada. Karmada really is mostly just scheduling the application and then monitoring what the health of that application is, in addition to monitoring the health of the cluster. But with regards to like additional metrics, that's something that you'll have to take care of within the individual Kubernetes cluster.
So it does not identify where the most resources are available, where to send the jobs and all?
Yes, so it does. There are a variety of different options when it comes to scheduling. The ones that we presented today rely on a component called the scheduler estimator. And what that does is it actually plugs into each individual cluster and will ping the destination namespace that you're applying your resource to, check the resource quota running on that namespace, and calculate how many replicas of your resource can fit into that namespace. So it calculates that for every single cluster, and then it decides to schedule your application to the cluster that has the most available replicas to schedule. So in that way, it evenly spreads your application across clusters.
And how about the storage? So the storage has to be synchronized across the clusters.
Could you clarify what you mean by storage?
Like your job, it processes some data, right? So where does the data store?
Okay. So for Apache Flink, we use an internal database, but that's spread and replicated across all the clusters and uses a unified endpoint. So for us, let's say whenever we fail over an Apache Flink application from cluster A to cluster B, the application is writing its state to that database from cluster A. And once Karmada reschedules the application, what happens is our webhook will actually call the same unified endpoint, which has read after write consistency, or guarantees, I mean. So once we're failed over, we can actually be certain that the latest state that has been written by the previous application will be fetched and can be injected into the new application.
And then I can add something for Spark. So there's also a section I was discussing in Spark about data locality done by the user when they want to launch a job. In Spark, it's quite common, especially those who are familiar with co-location in Yarn world of having your data be co-located. We are moving towards disaggregated compute, but if folks do prefer that speed up that comes from those production SLAs that they want for their Spark jobs, using the stretch constraints to make sure that you only go to one cluster and using cluster affinity rules, you can actually guarantee that you default to like where your data is stored, and then if that cluster is unavailable, then you have like a backup go to the other, other clusters. And so you can begin doing those clever data locality rules with the primitives that Karmada provides. That answers the question on the storage. Otherwise, we're happy to take questions offline as well. But thank you, everyone, for coming. Appreciate it.